Hello and welcome to the exercise session on how to calculate the chemical oxygen demand. So the first thing that we're going to do is look at a general formula of how to calculate the chemical oxygen demand of an organic compound. So, general formula. So, for our organic compound is normally composed of carbon, and we're going to say that there are n moles of carbon within this organic compound. There is hydrogen, and we are going to say that there is A moles of hydrogen but within 1 mole of this organic compound. And finally there's also oxygen, and we're going to say that there is B moles of oxygen within 1 mole of the organic compound. So to find the chemical oxygen demand, we need to find the number of moles that are required to oxidize 1 mole of the organic compound into carbon dioxide and water. So we'll write the chemical formula here. So it's the organic compound plus oxygen producing carbon dioxide and water. So what we need to do now is balance this chemical formula for carbon, hydrogen and oxygen. So let's start with carbon. So on the left side we have carbon present in the organic compound, and there is n moles of carbon within this organic compound. And then on the right hand side we see that carbon is present within carbon dioxide. And so in order to balance it, we're going to say that there is n moles of carbon dioxide. Therefore, we have n moles of carbon on the left and also n moles of carbon on the right. Next, let's have a look at hydrogen. So within our organic compound, we have A moles of hydrogen. And then on the right side, we see that there is hydrogen present in water. So in order for the left and the right side to be equal, we need to have A on 2 moles of water. So that we have 2 times A on 2 moles of hydrogen, which means that we now have A moles of hydrogen on the left and A moles of hydrogen on the right. And lastly, we are going to look at oxygen. For the time being, we're going to put an X for the number of moles of oxygen required, and we'll solve for this a little bit later. So first of all, we have B moles of oxygen within our organic compound. We have 2X moles of oxygen within oxygen and then we have 2n moles of oxygen within carbon dioxide on the right side, and then we have A on 2 moles of oxygen within the water. So for our left and right to balance, we have B plus 2x on the left side, and then we also have 2n plus A on 2 on the right side. So the question that we're going to be answering now is the number of moles of oxygen required to oxidize 1 mole of the organic compound that is represented by CnHAOB. So we need to solve for x. So we have B plus 2x is equal to 2n plus A on 2. So making the x the subject, we have 2n plus A on 2 minus B, and that all divided by 2. Now for simplicity's sake, we're going to times the numerator and the denominator both by 2. So then we get the general formula of 4n plus a minus 2b divided by 4. So we now can rewrite on a new page our general formula. So we have CNHA 0b plus the formula that we just created, which is 4n plus a minus 2b divided by 4 moles of oxygen, producing n moles of carbon dioxide and A on 2 moles of water. So this is our generic formula. We can now use it to calculate a specific example. So the exercise that we're going to now look at is a wastewater treatment plant receives water containing 100 milligrams per litre of glucose. And the chemical formula for glucose is C6H12O6. So within 1 mole of glucose there's 6 moles of carbon, 12 moles of hydrogen and 6 moles of oxygen. So the question is, what would be the chemical oxygen demand concentration in the effluent? In the influent. Okay, so we have 3 major steps that we're going to take in order to answer this question. So the first step, step 1, is to establish a molar ratio between oxygen and glucose. So how many moles of oxygen are required? Per mole of glucose. And the second step that we're going to do is then relate that to a mass balance by timesing by the molecular weight. So we then will have a mass ratio. And so that will be grams of chemical oxygen demand per gram of glucose. And the final step is then to determine the concentration based on the knowledge that we have 100 milligrams per litre of glucose in the influent. Okay, so let's firstly start with step 1. So that's the mole ratio. So let's quickly write the chemical formula. So we have glucose, which is C6H12O6, and that is oxidized to produce carbon dioxide and water. So we knew here N is equal to 6, A is equal to 12, and B is equal to 6. So we know that there was N moles of carbon dioxide, which means there are 6 moles of carbon dioxide, and there was A divided by 2 moles of water, so that means there's also 6 moles of water. And we have the formula to calculate the number of moles of oxygen required, which was 4n plus A minus 2b divided by 4. And if we sub the numbers in, we get 4 times 6 plus 12 minus 2 times 6 divided by 4, and that is equal to 6. So it's also 6 moles of oxygen required per mole of glucose. So our mole ratio is 6 moles of oxygen required to oxidize 1 mole of glucose. So that is step 1 completed. We can now move on to step 2 on a new page. So step 2 is the mass ratio. So first of all, we need to work out the molecular weight of glucose. So we've got the formula for molar mass. C6H12. We know that the molecular weight of carbon is 12 grams per mole. We know the molecular weight of hydrogen is 1 gram per mole. And we know the molecular weight of oxygen is 16 grams per mole. The molecular weight of any compound can be found using a periodic table. So we have the mass of 1 mole of glucose equal, so there's 6 moles of carbon within 1 mole of glucose, so we've got 6 moles of carbon times the molecular weight of carbon, which is 12 grams per mole. And then we also have 12 grams of hydrogen, so 12 times 1 gram per mole. And then we also have 6 grams of oxygen, which is 16 grams per mole. So there is 72 grams of carbon within 1 mole of glucose. And 12 grams of hydrogen within 1 mole of glucose. And 96 grams of oxygen in 1 mole of glucose. Summing these all up, we get 180 grams per mole of glucose. So next we need to look at the molar mass of oxygen. So 1 mole of oxygen so there's 2 oxygen so it's 2 times 16 grams per mole, which equals 32 grams per mole of oxygen. So then we can now relate this to a ratio. So we have 6 moles of oxygen per 1 mole of glucose. And then if we also then times by the molecular mass, so that's 32 grams per mole of oxygen, and then there's 180 grams per mole of glucose. We find that there's 1.07 grams of COD per gram of glucose. With this knowledge, we can then move to our final step, step 3 on a new page. So that is to calculate the concentration. So, to find the COD concentration, which is measured in milligrams per litre, we knew that the influent had 100 milligrams of glucose per litre of the wastewater, and now we times that by our mass ratio, which we just calculated in step 2, so that's 1.07 milligrams of COD per milligram of glucose. And summing those two together, we get 107 milligrams of COD per litre of wastewater.